Dear friends, Maths Aspirants is a collective of mathematics students, research scholars, faculty members across India initiated by myself in 2017, and we used to organize several online programs to help the students who are preparing for different national level competitive examinations and interview preparations. Today, we blessed to have Miss Ardra AM to handle a session on linear algebra. Ms. Ardra is currently a research scholar at Hyderabad Central University, and her research area is algebraic graph theory. Ardra did her MSc from University of Calicut, Kerala, and I would like to express my gratitude to Ms. Ardra for joining with Math Aspirants. I welcome everyone to this program. I'm sure that as linear algebra is one of the important topic in any competitive examinations in higher mathematics, I'm sure that today's session will be really helpful to revise the concepts and also to boost your preparations for exams. So I request all the participants to actively involve in the session, and I welcome again everyone again to this program. Welcome, Ardra.
So good morning, everyone. First of all, I would like to thank Vinod sir for giving me this opportunity. Thank you, sir. So as sir has mentioned, linear algebra is one of the important topics for competitive exams. So in today's session, I will be discussing some of the important concepts and questions related to linear algebra. My main focus is for IIT JAM. However, it will be a revision session for other aspirants also, like CSIR, NET, GATE and all. So you can just brush up the basics and practice the questions. So you can just see the mark distribution of linear algebra here. For IIT JAM, the weightage is approximately 14 to 16 marks. And for CSIR, NET, JRF, it's approximately 56 marks. And for GATE also, it's approximately 10 marks. So linear algebra is one of the important topics. So as I have mentioned, my main focus is for IIT JAM. And here are the important topics of linear algebra for IIT JAM. There are two sections. One is matrices and another is finite dimensional vector spaces. So in today's session, we will be just sticking to the section of matrices. That is, we will be dealing with the questions related to system of linear equation, rank, nullity, inverse, determinant, eigenvalues, and eigenvectors. So one of the important goal of linear algebra is developing effective techniques of solving system of linear equation. That is, suppose 2x plus 3y plus 4z is equal to 3 and 4x plus 6y plus 5z is equal to 6. Then the question comes whether there exists x, y set satisfying these two conditions. If such x, y set exists, then the next question is, are these values unique? So for solving the system of linear equation, there are two ways. One way is through the theory of matrices and the another way is through the theory of linear transformation. But in today's session, we will just stick to this theory of matrices part. That is, we will be formulating this system of linear equation into a matrix equation, and we will be solving this system using the properties of matrices. Okay, so I have collected past 5 question papers of IIT JAM, and so we will discuss the questions. Simultaneously, we will discuss the concepts and important results related to that question. So let us start with simple question. This is a question from JAM 2022. You can just try. I will give 1 to 2 minutes is enough, I think. Yes, correct. 4 is the correct answer. So can I start discussing? It's a simple question only. So The question is finding the rank of the matrix. So let us discuss the definition of rank. So for a matrix A, M by N matrix, the rank is defined like this. Many definitions are there. One definition is it is the order of the largest non-singular square submatrix of A. Second definition is the number of linearly independent rows or columns of A. Third one, the dimension of the row space or column space of A. Fourth one is that the number of non-zero rows in the row reduced echelon form of A. Fifth one, the order of the identity submatrix in the normal form of A. And sixth is the rank of the linear transformation from Rn to Rm corresponding to the matrix A. So let us take this fourth definition so that we can recall the definition of row reduced echelon form also. So what is a row reduced echelon matrix? An M by N matrix R is said to be in row reduced echelon if the first non-zero entry in each non-zero row of R is equal to 1. And the second condition says that all the other entries in that column, that means each column of R which contains the leading non-zero entry of some row has all its other entries 0. And third condition says that every row of R which has all its entries 0 occurs below every row which has a non-zero entry. And the fourth condition is that if rows 1, 2, etc. R are the non-zero rows of R, and if the leading non-zero entry of row I occurs in column Ki, then K1 less than, K2 less than, etc. Kr. So let us take our matrix. This is the matrix. So here we can see that first row, first column is 1. So to make it row reduced echelon form, we have to make all the other entries here 0. So we are operating like R2 is changing to R1 minus R2. We can just do that. So we are getting all the other entries in this first column 0. Now we go to the second row, second column. So second row, second column, it is 1. Now we have to make all the other entries 0. So we are just operating like either R1 changes to R1 minus R2 or R3 changes to R3 minus R2. Some operations we are doing and we are making all the other entries 0. And then coming to the third column is minus 1, but we need 1. So we are multiplying or dividing it by minus 1. So we are getting this matrix. Now we want to make these two entries 0. So we are doing some elementary row operations and we are getting this matrix. And now the fourth column is 2, but we need 1. So we are dividing this row by 2 and hence this is the matrix. And all the other entries in the column must be 0. So again, we are operating and we are getting this matrix. So this is the row reduced echelon form of the given matrix, this one. So here the definition, according to the definition of rank, it is the number of non-zero rows in a row reduced echelon form of the matrix. So here we can see that there are 4 non-zero rows in this row reduced echelon form and hence the rank is 4. So answer is option D. I hope that the answer is clear. Can we move to the next question?
Yes.
Okay. So here is a question from JAM 2023. You can just try. Any other answers? Okay, so let me start explaining. So here we are given a matrix A and a matrix B, and it is given that AB is a zero matrix. So the question is about the maximum possible rank of the matrix B. So first let us recall the Sylvester's inequality. The Sylvester's inequality says that if A is a M by N matrix and B is an N by P matrix, then rank of A plus rank of B minus N is less than or equal to rank of AB. So from this matrix, what is the rank of A? Can anyone tell what is the rank of A?
3.
Yes, 3. Yes, rank of A is 3. And here N is equal to 5. So just substitute those values. And since AB is the zero matrix, rank of AB is 0 only. So just substitute these values in the inequality. So we will get 3 plus rank of B minus 5 is less than or equal to 0. So this implies that rank of B is less than or equal to 2. That is the maximum possible rank of B is 2. Is the solution clear?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. So now we know another inequality also regarding rank of AB. What is that? Anyone? Rank of AB is less than or equal to?
Minimum of rank of minimum.
Yes, yes. So combining this Sylvester's inequality and that inequality, we will get this result. If A is a M by N matrix and B is an N by P matrix, then rank of A plus rank of B minus N is less than or equal to rank of AB, which is less than or equal to minimum of rank of A comma rank of B. Okay. So similar to this concept of rank, we have another important concept, nullity of a matrix. Nullity of a matrix is the dimension of the null space of a matrix. So what is null space of a matrix? Suppose A is an M by N matrix, then null space of A is equal to set of all X belongs to Rn such that Ax is equal to 0. So the question comes whether there is any relation between rank and nullity of a matrix. So yes, we have a rank nullity theorem which says that for any matrix A, rank of A plus nullity of A is equal to number of columns of A. Okay. So let us come to the system of linear equations. So this system we have seen in the beginning slides. So this is a system with 2 linear equations and 3 unknowns. So we are converting it into a matrix equation. We are just taking the coefficients of X, Y, Z. So 2, 3, 4 in one row and 4, 6, 5 in another row. And X, Y, Z, it's a column matrix, and this 3, 6 is also a column matrix. So we are getting a matrix equation Ax equal to B, where A is a 2 by 3 matrix and X is a 3 by 1 matrix and B is a 2 by 1 matrix. So that is, let A be an M by N matrix, X be an N by 1 matrix and B be an M by 1 matrix. Then the matrix equation Ax equal to B represents a system of M linear equations in N unknowns, where this A is the coefficient matrix because we are forming this matrix by taking the coefficients of these unknowns. So A is the coefficient matrix and X is the unknown matrix and B is the constant matrix. So now we got a matrix equation from system of linear equation. Now, what we can say about this system using this property of matrices? So we have cases. The first case is that suppose this Ax equal to B with B not equal to 0. Then such a system is called non-homogeneous system. And this system has a unique solution if and only if rank of A is equal to rank of A adjoint B, that is equal to number of unknowns. And it has if suppose rank of A is equal to rank of A adjoint B, but suppose the rank is strictly less than the number of unknowns, then we will have infinite number of solutions. Okay. Now suppose this rank of A is not equal to rank of adjoint A adjoint B, then we have no solutions. Okay. So this A need not be a square matrix, but suppose A is a square matrix, then this has a unique solution if and only if determinant of A is not equal to 0. And it has an infinite number of solutions if and only if determinant of A is equal to 0 and adjoint of A into B is equal to 0. And it has no solution if and only if determinant of A is equal to 0 and adjoint of A into B is not equal to 0. So this is the concepts related to non-homogeneous system. This is the results. Suppose this B is equal to 0. That means we have the system AX equal to 0. So such a system is called homogeneous system. And this system has always one solution, at least one solution it will have. That is, if we are just taking all the unknown to be 0, that is, if X is equal to 0, then we will get A into 0 matrix equal to 0. So 0 is always a solution, and this solution is called the trivial solution. So in case of homogeneous system, we always have a solution. So the only question comes is whether it is a unique solution or infinite number of solutions. So it will have a unique solution if and only if rank of A is equal to the number of unknowns. And suppose the rank of A is strictly less than the number of unknowns, then it will have infinite number of solutions. Okay. So as a particular case, we can say if A is a square matrix, then it will have a unique solution if and only if determinant of A is not equal to 0. And it will have infinite number of solutions if and only if determinant of A is equal to 0. So if you want to take screenshot, you can take. So let us go through the questions related to this system of linear equations so that you will get thorough with this result. So this is a question from JAM 2025. You can take 2 to 3 minutes to solve this question. You can try. Yes, I will share the material after the class. Okay. Yes. So you have, so many have answered option A. Yes, option A is correct. Good. So can I start explaining? Yes, so 1 minute. So here, uh, we are given a matrix M, and they are asking the question about the rank of the matrix and about the system of these linear equations. So we are just taking the matrix M, and we are reducing it into row reduced echelon form, and hence we are getting a matrix like this. So what is the rank of the matrix M? 3. Yes, 3 is the rank of matrix M. Now they are asking about this system. So which is the system? Is it non-homogeneous or homogeneous?
Non-homogeneous.
Yes, non-homogeneous. So we have to take the A adjoint B matrix. So this one is the this one is the M matrix, and this one is the B matrix. So we are adjoining this M with B matrix. So what is the rank of M by B matrix?
3.
3. So we got that rank of M matrix is 3, as well as rank of M adjoint B matrix is also 3. So here we have first option. So rank of M is 3. So we can just discard option C and option D. Now option A says that the system has a solution, and option B says that S doesn't have a solution. But now we got that rank of M adjoint B is equal to rank of M. So it will have a solution, isn't it? And it is equal to 3, which is strictly less than 4. So it will not have a unique solution, but it will have infinitely many solutions. And hence, the answer is option A. Is the solution clear? Any doubt?
No, ma'am.
Okay, so we can move to the next question. This is a question from JAM 2023. B and D, it's an MCQ question. Okay. Yes, so many have answered option B. Yes, option B is correct. So let us see the solution. So here we are given a system of linear equations, and in that two unknowns are there, alpha and beta. So they are asking, they are giving some conditions on alpha and beta and asking about the system of linear equation. So first we have to consider the matrix 1, 1, 1, 3, and we are adjoining the constant matrix also. So 1, 1, 1, 3, 0, minus 1, 1, 1, 2, 3, alpha, beta. So we are we are doing some elementary operations and we are getting a matrix like this. Now we have in the third row, we have alpha minus 1, beta minus 5. So this alpha and beta will decide the behavior of the system of linear equation. Okay, so why option A is wrong? Why option A is yes?
If alpha equal to 1, it has no solution.
Sorry, can you repeat?
If alpha equal to 1 and beta is not equal to 5,
Yes. Then
it has no solution.
yes, then it will not have solution. Suppose alpha is equal to 1. Then what will be this rank of this matrix?
2.
Yes, it will be 2. And the rank of this adjoint matrix will be 3 because beta, if beta is not equal to 5. Yes, so rank of A and rank of adjoint of AB is not same. So we have then we will not have a solution. And hence it will not have a solution in the first case, option A. And if alpha is not equal to 1, then the rank of this matrix, rank of the matrix A and the rank of matrix A join B will be same only, it will be 3. And here we have 3 unknowns. So that means the rank of the matrix is same as the number of unknowns and hence it will have a unique solution. What about option C? What about option C? Which value of alpha we can take? Suppose alpha is not equal to 1. Then we will get this matrix. Rank of this matrix will be 3. Isn't it? So we will have unique solution only. So it will have a solution. So option C can't be correct. And similarly, suppose so option D says that it has infinitely many solutions for any alpha. No. Suppose this alpha is not equal to 1. Then we will have rank of A and rank of A adjoint B is equal to 3, which is equal to number of unknowns, and hence it will have unique solution only. So option C and D can be discarded. And hence option B is the correct answer. Any doubt?
Hello, ma'am.
No, ma'am.
Okay. So we can move to the next question. So this is a question from Jam Chandranipri. So actually in the system of linear equation, you just have to focus on the reducing this matrix. So we have to be careful while reducing this matrix. Only that process is important. From that we can analyze about the system of linear equations. So we have to be careful while reducing the matrix. Yes, D is the correct answer. Yes. So many have answered correct. Good. So we can move to the solution. So here we are given 9 column vectors v1, v2, etc. v9, and they are the column vectors of a non-zero real matrix A. And let a1, a2, etc. a9 belongs to R, not all 0 be such that summation of I is equal to 1 to 9, ai vi is equal to 0. Then the system ax equal to summation I is equal to 1 to 9 vi has. So first consider the system. What is the system? Is it homogeneous or non-homogeneous? Summation I is equal to 1 to 9, ai vi is equal to 0. Anyone?
Homogeneous.
Yes, it is homogeneous system. Yes, it's homogeneous system. So we have, hence we have seen that for a homogeneous system, there exists always one solution. So either it will be unique or it will have infinitely many solutions. So if it is unique means, then the trivial solution is the solution. But if it has infinitely many solutions, then it will have some non-zero solution. Okay. So here it is given that a1, etc., a9, not all 0 is a solution of the system. So that means it has infinitely many solutions, isn't it? Because a1, etc., a9, not in that case, all are not 0. Not all are 0. So we will have the system. The system has infinitely many solutions. So what will be the rank of this matrix A? Can you say anything about this rank?
Less than or equal to 9.
Less than 9.
Less than 9. It will be less than 9, or we can be less than or equal to 8, we can say. Yes. So we will get that rank of A is strictly less than 9. Now the question is about this non-homogeneous system. Ax is equal to summation I equal to 1 to 9 Vi. Vi are the column vectors of A matrix. So since Vi are the column vectors of matrix A, we will get that the rank of A adjoint V is equal to rank of A. And rank of A, we know that it is strictly less than 9. That means it is not equal to the number of unknowns. So we will have infinitely many solutions. And hence the answer is option D. Is it clear?
Yes, ma'am.
Yes.
Okay. Yes, ma'am. Okay. So can we move to the next question?
Yes.
Okay. So this is a question from JAM 2021. This is a MSQ question. So analyze each option carefully. Okay, so I can see different answers. Anyway, everybody is saying that A is correct. So what about B, C, D? That is in doubt, I think. So let us start solving this question. So we have a matrix A, M by N matrix, such that for some M by 1 matrix V1, the equation Ax equal to V1 has infinitely many solutions. Okay. So Ax equal to B1 has infinitely many solutions means what we can say about the rank of the matrix A and AB?
Less than M.
Less than?
M.
Less than M or less than N? What is the number of unknowns here?
N.
N. So the rank of A is equal to rank of AB will be less than N, right? It should be less than the number of unknowns, isn't it? Yes, so the equation Ax equal to B1 has infinitely many solutions means the rank of AB1 and rank of A, this will be same because it has a solution. And it has infinitely many solution means this rank will be strictly less than the number of unknowns, and the number of unknowns here is N because it is A is M by 1, M by N matrix. So the X will be a N by 1 column matrix. Sorry, yes, N by 1 column matrix. So rank of A, B1 is equal to rank of A is strictly less than n. Now let us analyze each option. So the question is about the system AX equal to B2, where B2 denote an m by 1 matrix different from B1. So AX, so what about first option? Can you say one B2 for which it has an infinitely many solution?
If last element of the V2 is 0, then it may have infinitely solution.
Last, can you repeat?
If the rank of A
Rank of
and augmented matrix AB and rank of A is equal and they are less than n, then it may have infinitely solution.
Yes. So can you say some particular B2 for which this will hold? Can we take like 2B1? If B2 is equal to 2B1?
Yes, ma'am.
Yes. So if B2 is some scalar multiple of B1, and it should not be 1 because it is given that B2 is different from B1. So if B2 is 3B1 where C is not equal to 1, then AX equal to B2 has infinitely many solutions. Okay. Now, what about option B? We have for option B to be true. That means if AX equal to B2 have unique solution, if and only if this rank of A is equal to rank of A B2, augmented matrix A B2 is equal to number of unknowns. But here we got that the rank of A matrix is strictly less than n. So it will not have unique solution. For unique solution, this rank of A must be equal to n, and hence unique solution possibility is not there. So option B is wrong. Okay. So for option C, we can choose B2 such that rank of A is not equal to rank of A adjoint B2. If rank of A is not equal to rank of A adjoint B2, then we have that it will not have a solution. So option C can be true. But in case of D, so here we got that rank of A is strictly less than n. So the only possibility is either it will have solution, either it will have infinitely many solution, or it will not have a solution. So there is no case of finitely many solutions. So and hence option D is also wrong, and hence option A and C are correct. Is the solution clear?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. So we are moving to the next question. This is a question from JAM 2022. So no answers. Okay, try. Yes. Yes, C, correct answer. Let us wait for some other answers also. Yes. So let me start explaining. So yes, answer C, option C is correct. So here we are given a system of linear equation, and in that lambda is unknown. That means lambda is unknown. So based on this lambda, they have given some questions like, if lambda is 1, then what will be the behavior of the system, and if lambda is 2, what will be the behavior of the system. So first we have to make into a matrix. So this is the matrix that we have formed from the system, and this is the matrix equation, and we are reducing this matrix into this form. So this is the reduced matrix of the given linear system of linear equation. So here we can see that in the fourth row, we have lambda minus 1. So depending upon this lambda, we can know the behavior of the system. So suppose lambda is equal, so here the rank of this matrix is fixed. That means the rank of this matrix A is, what is this rank of the matrix A? I'm taking this coefficient matrix A. So what is the rank of the matrix?
3.
3.
Yes, 3. So depending upon this lambda, we will get rank of A adjoint B. So suppose lambda is equal to 1. If lambda is equal to 1, then the rank of A adjoint B matrix will be 3 only. And this 3 is strictly less than 4 because here we have 4 unknowns, x, y, z, t. So this rank of A is equal to rank of AB is equal to 3, which is strictly less than 4. So we will get that it has infinitely many solutions. So if you are taking option A and C, we will get that if lambda is equal to 1, it has infinitely many solutions. So option A is wrong and option C is correct. Then what about if lambda is equal to 2? If lambda is equal to 2, then rank of A is already fixed. It is 3. And rank of this A, B matrix is equal to 4 if lambda is equal to 2. So if rank of A is not equal to rank of AB, then we have no solution. So option B is also false and option D is also false. It will not have a solution. And hence option C is the correct answer. I hope that the solution is clear.
Yes, ma'am.
Okay. So in this system of linear equation, you just have to make the a matrix equation, or you have to just form a matrix from the system and be careful while reducing it. And if some mistakes come, then it will affect the analysis. So just be careful while reducing. All other things are fine only. So this is a question for just practice. You can take the screenshot and you can try it later. Here it's a matrix is given P, and it's asking a question about the Px equal to C matrix equation. Okay. So you can take the screenshot. This is also a question. You can try it later. Here we have a system AX equal to 1, 0, minus 1. Then they are asking some questions related to consistency and singular. What is meant by a system to be consistent? Or when a system is said to be consistent?
If it
If it
has
has a
solution.
unique solution, yeah, infinite solution.
Yes, if it has a solution, then it is a consistent system. And what about singular? I mean, when a matrix is said to be singular,
Determinant is 0.
yes, determinant is equal to 0. So just using that concepts, try this question. And I have given the answer also. You can just try and verify the answer. Okay, so let us move to the another concept, eigenvalues and eigenvectors of a matrix. So for that, we need characteristic polynomial first. So suppose A belongs to Mn of F, where F is an arbitrary field, that is A is an n by n matrix, where the entries are from the field F. Then the characteristic polynomial of a square matrix is given by determinant of xi minus A. And the characteristic equation of a square matrix is that psi a of x is equal to determinant of xi minus A is equal to 0. And from this, we have an important theorem, an interesting theorem, that Cayley-Hamilton theorem, which states that every square matrix satisfies its characteristic equation. That is, psi a of A is equal to 0. So similar to the characteristic polynomial, we have another important polynomial, minimal polynomial. Minimal polynomial is, let J of x be the collection of all polynomials in X for which A is a root. A matrix A is a root. That is, J A of x is equal to set of all P of x belongs to F of x such that P of A is equal to 0. Then minimal polynomial is the least degree monic polynomial in J of x, which divides every elements of J of x. Okay, and it is denoted by MA of x. So from this, we will get that this minimal polynomial will divide the characteristic polynomial. Okay. So now, what is an eigenvalue and eigenvectors of a square matrix? So we have two definitions. First definition is that let A be a m by mn of f and let lambda belongs to f. Then lambda is said to be an eigenvalue of A if there exists a non-zero vector x belongs to fn such that Ax is equal to lambda x. Such an x is called an eigenvector corresponding to the eigenvalue lambda. So this is one definition. That means we need a non-zero vector x such that Ax is equal to lambda x. Okay. And the second definition is using the characteristic polynomial. Let A belongs to Mn of x and this is capital F, field F, and let psi a of x be the characteristic polynomial of A. Let lambda 1, lambda 2, etc., lambda n need not be distinct, be roots of the characteristic polynomial. Then lambda I are called eigenvalues of A if lambda I belongs to F. Okay, so we have two definitions of eigenvalues. So depending upon the question, we have to switch between these definitions. Sometimes we have to use this first definition, and in other times we may have to use the concept of characteristic polynomial. So we will see these in the coming questions. So similar to
यहाँ पे lambda 1 and lambda 2 यहाँ need not be distinct.
need not be distinct.
Okay.
So because every polynomial will have, n degree polynomial will have n solutions and n roots. So these n roots may not be distinct. So similarly, lambda 1, lambda 2, lambda n need not be distinct. And whether it is a eigenvalue depends upon if lambda I belongs to this capital F. So related to this eigenvalue concept, we have another concept like eigenspace, algebraic multiplicity, and geometric multiplicity. So what is an eigenspace? So for eigenspace of a eigenvalue lambda is the subspace of f raised to n given by, this is the notation of eigenspace corresponding to this eigenvalue lambda. E lambda is equal to set up for x such that a minus lambda I of x. Here is x is lambda I of x is equal to 0. Or it is the null space of a minus lambda I. Or we can say that E lambda is the null space of a minus lambda I. Okay, here x is missing. So this is the definition of eigenspace. And coming to the algebraic multiplicity and geometric multiplicity, algebraic multiplicity of a eigenvalue lambda is the multiplicity of this lambda as a root of the characteristic polynomial. So maybe characteristic polynomial will have lambda, and lambda will have multiplicity 2 or 3. So that is the algebraic multiplicity. That is multiplicity of lambda as a root of the characteristic polynomial is the algebraic multiplicity. And the geometric multiplicity is the dimension of this eigenspace E lambda. Okay. And also we have another definition of GM, geometric multiplicity of lambda is the number of linearly independent eigenvectors corresponding to this lambda. Okay. So here we have another result, means we have another important result regarding this eigenvalues. Determinant and trace of a matrix can be evaluated using the eigenvalues of a matrix. The determinant of a matrix is the product of all its eigenvalues, and trace of a matrix is the sum of all its eigenvalues. Okay, so many concepts are, these are just the basic concepts. Many concepts are there related to eigenvalues. We will have means we have different types of matrices like idempotent, nilpotent, and all. So for all these matrices, we have the eigenvalues have some properties. So due to the time restriction, I'm not going deep into that. But while discussing the questions, I will revise some of the properties of some matrices and all. So let us see how the questions are coming related to eigenvalues and eigenvectors. So this is a question from JAM 2021. We have to find the determinant of this matrix. So we have, by seeing this matrix, it seems like big matrix, means entries are large numbers. But we have just now we have seen a result relating determinant and eigenvalues. So try to use that and try solving. The converse part of Cayley-Hamilton theorem means the Cayley-Hamilton theorem says that every square matrix satisfies characteristic polynomial or characteristic equation. So the converse means suppose there exists a polynomial. Suppose there exists a polynomial p such that p of a is equal to 0. Then this p need not be the characteristic polynomial. Is that what you have? What you are asking about the converse part of Cayley-Hamilton theorem? A polynomial equation. So it need not be a characteristic polynomial. A polynomial satisfying. No. even the minimal polynomial is satisfying this equation. If P is a minimal polynomial, then P of A is equal to 0. Okay, so many have answered the option. Many have answered. The answer is 2021. Yes, it is correct. Good. So let us move to the solution. So we have given a matrix. So whenever we get such a matrix, we have to think about whether we can reduce into some symbol matrix or some particular matrices like idempotent, nilpotent, Rangman matrices and all. So here, to which matrix we can reduce it? Can anyone say how you found this determinant?
Triangular matrix plus lower triangle.
Yes, correct. Good. So we are reducing this matrix into a triangular matrix. So here we have a result. Even if we are doing some elementary row operations or column operations, the determinant is remaining same. Determinant of A double dash is equal to determinant of A, where A double dash is the matrix obtained from A by operating like Ri changes to Ri plus or minus Krj, I is equal to J. Okay, I is not equal to J. And here also we can see that column also we can do the similar operation. Here actually it is I not equal to J. Okay. So here we are doing some elementary operations and converting this matrix into a upper triangular matrix. And we know that eigenvalues of a triangular matrix are its diagonal elements. So here, what are the eigenvalues of this matrix?
2021 and 1.
2021, 1, 1, 1. So these are the 4 eigenvalues. And hence, we know that determinant of a matrix is equal to the product of its eigenvalues. So we will get that 2021 into 1, 1, 1. So 2021 is the answer. I hope that the answer is clear. So,
Yes, ma'am.
okay. So whenever we get such matrices, we have to think about how whether we can reduce it into some particular matrices or not. So similarly, let's take this example. Finding the question is to find the determinant of this matrix. So in this matrix, only all the diagonal elements are 2026 and all the other entries are 2025. So we are just splitting this matrix like here in this matrix, all the entries are 2025 and this is the identity matrix. Okay. So what is this matrix? Can anyone say this first matrix? Is it idempotent, nilpotent, or some other? Is it rank 1 matrix?
Yes.
Yes, ma'am.
Yes. Yeah, so what can you say about the eigenvalues of a rank 1 matrix?
1 minus
0,
1
0, 0,
eigenvalue
10 to
0.
Yes, correct. N minus 1 eigenvalues will be 0 and one non-zero eigenvalue is the trace of the matrix. So here the eigenvalues are 0, 0, 0 and the last one is 20, 25 into 4, that is 8100. And this is the identity matrix and the eigenvalues of identity matrix are 1, 1, 1, 1. And hence now we have another result. Eigenvalues of the matrix A plus I are the eigenvalues of A plus 1. So here we have the eigenvalues 800, 8100, 0, 0, 0. And the eigenvalues of identity are 1, 1, 1, 1. So the eigenvalues of the given matrix will be 8100 plus 1, 1, 1, 1. So the determinant will be 8100 plus 1 into 1, 1, 1. Okay. Is it clear? Any doubt?
Yes, ma'am, clear.
Okay. So let us see some other questions related to characteristic polynomial. So this is a question from JAM 2024. Here we are given a matrix M. And if P of X is the characteristic polynomial of M, then P of 2 minus 1 equals. I'm minus 1 instead of 1. Which last question? Question number 10. But it is 1, right? Eigenvalues are 2021, 1, 1, 1. If we are just converting it into triangular matrix, we are getting like that, diagonal elements. Still the eigenvalues will satisfy that polynomial. Eigenvalues means all the eigenvalues of the matrix must be the roots of the minimal polynomial also. Yes, 31. You can just check whether this matrix M is similar to some of our non-matrices. And so we will get the characteristic polynomial easily and hence we can calculate P of 2 minus 1. Yes, it's similar to companion matrix. So I am just starting solving this equation. So the question is about the characteristic polynomial of the matrix M. So this M is looking like this matrix, right? And the name for this matrix is companion matrix, where the second row first column is 1, and third row second column is 1, and like that we are getting. And in this last column we have minus a n minus 1, like that and all. So this matrix M is similar to this matrix, and this matrix is companion matrix. And we know the characteristic polynomial of a companion matrix. Characteristic polynomial of a companion matrix is x raised to n plus we are taking the last entry of the last column plus an minus 1 x raised to n minus 1, then plus an minus 2 x raised to n minus 2 plus etc. And the coefficient of x will be the second row entry in the last column, that is a1x, and the constant term is plus a0. Okay, so this is the characteristic polynomial of a companion matrix. But our matrix is not in this form, but we can make it into a companion matrix form. So what we have to do? We just have to take this 2 from outside. So 2 from inside. So just take 2 outside. So we are getting this matrix, and this is equal to 2 times A. And now the characteristic polynomial of M, P of x, is equal to determinant of M minus xi. And we have this M is 2A. So determinant of 2A minus xi, which is equal to 2 power 5 determinant of A minus x by 2i. And this A matrix is companion matrix. So we just have to take the characteristic polynomial of A, so 2 power 5 of x by 2 power f. And what is the coefficient of x by 2 power f, power 4? It is minus 1. So minus x by 2 raised to 4. And the coefficient of x cube is, x by 2 cube is minus 3 by 2. So minus 3 by 2 x by 2 cube. And the coefficient of x by 2 square is 0. So we are not taking that. And then the coefficient of x by 2 is plus 2. So plus 2 into x by 2. Then the coefficient of the constant term is plus 1 by 2. So this is the characteristic polynomial of A. And hence we just have to find the P of 2 minus 1. So just substitute 2 here. So you will get 31. Is the technique clear? Any doubt? It's not minus 1, it's 31. Huh?
If we rearrange this matrix into an upper triangular matrix, then can we solve this?
Upper triangular matrix. So how you are getting this? I haven't tried that. So
If R1 changes to R1 and R2 are interchanged.
R1 and R2 are interchanged.
Then R5 and now R2 are interchanged.
Which
So
one?
we may get
Is it? But I think maybe some mistakes may happen while rearranging the problem. Are you getting an upper triangular matrix?
yeah.
Okay, so R1 changes to
At first, R1 and R2 are interchanged.
Okay, R1 and R2 are interchanged.
Then the given R2 is changed
Uh,
to R3, interchanged with R3.
But actually,
And then
if you just see this result, the determinant will remain same only if you are doing this operation. Ri plus or minus Krj. So I think some mistake will come if you are.
if we interchange two rows or columns, then the determinant will be negative of the actual determinant, isn't it?
Yes, yes, yes.
So there we need a 4 times interchanging. Then the resultant determinant will be same as the first actual determinant. Then we get x minus 2 whole raised to 4 into x plus 1 is the characteristic polynomial of the given
With
matrix.
Okay, x minus 2
whole raised to 4 into x plus 1.
X plus 1. Okay. So I will check and I will say it later. Is it okay?
Yes, ma'am.
मैम इससे भी हो जा रहा है 31 आ रहा है इसमें भी
31, हाँ.
जी भाई सही कर रहे हैं ऐसे भी हो जाएगा
Okay.
क्योंकि 4 टाइम्स अगर मल्टीप्लाई नेगेटिव से करेंगे तो वो ऑब्वियसली वो पॉजिटिव आ जाएगा ठीक वैसे भी कर सकते
Okay. Anyway, I will check that and I will inform you later. Okay. Maybe some mistakes will come, I think. Anyway, I will try. Okay. So let us move to the next question. See, question from JAM 2025.
मैं भूपेश सिंह लिखवाल बात कर रहा हूँ।
So here we are given a matrix M and we have an unknown X, and they are given two eigenvalues of M and another condition also, M cube of 0, 1, 1 equal to 0, 1, 2, 5, 1, 2, 5. And they are asking about the value of X and about the M square plus M. Is it option A? Okay. Let us wait for some other answers also. Yes. B is the answer. So let us start seeing solution. So here we have two eigenvalues, -2 and -2 and 3. And we are given another condition also, like M cube of 0, 1, 1 is equal to 0, 125, 125. Okay. So here M cube of 0, 1, 1 is equal to 0, 125, 125. So you just take 125 outside. So what we got? M cube of 0, 1, 1 is equal to 125 into 0, 1, 1. So according to the definition of eigenvalues, we have two definitions. In that according to the first definition, we have 125 is the eigenvalue of M cube, right? Because we are getting a non-zero vectors 0, 1, 1, such that M cube of 0, 1, 1 is equal to 125 into 0, 1, 1. So 125 is an eigenvalue of M cube. And hence 5 is an eigenvalue of M. So we got the three eigenvalues, -3, -2, 3, 5. Okay. Now they are asking about x. So how to find x? So how to find x?
Sum
With
of
the help of
eigenvalues.
eigenvalues.
Yes. With the help of eigenvalues, we can find the value of x. We know that the trace of a matrix is the sum of its eigenvalues. So trace of M is equal to -2 plus 3 plus 5. And from matrix, we will get the trace is equal to -2. Trace of a matrix is the sum of its eigenvalues. So here -2 plus 2 plus x. So that is -2 plus 2 plus x. That is x is equal to 6. So x is not equal to 5. So option A and C are wrong. Now we have to consider option B and D. That is, what about the matrix M square plus M? So M square plus M is invertible or it is not invertible? That is the question. So we know that it is invertible if and only if its determinant is not equal to 0. And determinant is not equal to 0. How we can say about the determinant and eigenvalues? When will be the determinant of a matrix not equal to 0?
If the all eigenvalues are matrix are non-zero.
Yes. So we just have to analyze the eigenvalues of M square plus M. So here eigenvalues of M are -2, 3, 5. So the eigenvalues of M square are -2 square, that is 4, 3 square 9, and 5 square 25. Okay. And the eigenvalues of M square plus M are, you just have to sum it like 4 plus -2, 9 plus 3, 25 plus 5. That is, we will get the eigenvalues of M square plus M are 2, 12, 30, isn't it?
Yes, ma'am.
Yes. So the determinant of M square M is equal to 2 into 12 into 30. And all the eigenvalues are non-zero, and hence the determinant is not equal to 0. And therefore M square plus M is invertible. And hence option B is correct. Okay. So determinant of a matrix is 0. It means relating to eigenvalues, we can say that if all the eigenvalues of the matrix are non-zero, then the determinant will be non-zero. Okay. I hope that okay. I hope that solution is clear. So can we move to the next question?
Yes, ma'am.
Okay. So this question is also similar, like eigenvalue. We have to find which of the following is not an eigenvalue of B. We are given a matrix A. So you can try. Yes. B is the answer. So let me start explaining. You just have to compute the eigenvalues, that's all. So what are the eigenvalues of A?
1, 0, 2.
Yes, 1, 0, 2. And therefore, we can just compute the eigenvalue of A raised to 5. Eigenvalues of A raised to 5 will be 0, 1, 2 power 5. And the eigenvalues of A power 4 is 0, 1, 2 power 4. And eigenvalues of identity matrix is 1, 1, 1. And hence, just find the eigenvalues of A raised to 5 plus A raised to 4 plus I3. That is, it will be 0 plus 0 plus 1, comma 1, 1 plus 1 plus 1. Then 2 power 5 plus 2 power 4 plus 1. So we will get that the eigenvalues of B are 1, 3, 49. So hence option B is the correct answer. So let us move to the next question. This is a question from JAM 2025. Here also we have a matrix M, and in that matrix there is one unknown X, and we are given some condition about eigenvalue. That means 0 is an eigenvalue of M. Then we have to find the value of M raised to 4 plus M of 101. So if 0 is an eigenvalue of M, we can know something about determinant of M, right? Determinant of M will be
0.
yes, 0. So using that, you can find X also. Yes. Yes. So B is the correct answer. So let us move to the solution. So as 0 is an eigenvalue of M, determinant of M is equal to 0. So you can find the value of X, like 2X from this matrix, we can calculate the determinant and we will get that 2X plus 2 is equal to 0. So x is equal to -1. So we will get the m is equal to 2, 0, -1, 4, 1, -4, 2, 0, -1. And now you just multiply m with 1, 0, 1. So by calculation, you will get that m of 101 is equal to 101. So according to the definition of eigenvalue, we will get that since there is a non-zero vector 101 such that m of 101 is equal to 1 into 101. 1 is an eigenvalue of this matrix and 101 is an eigenvector corresponding to this eigenvalue. So m of 101 is equal to 101. And so we will get m raised to 4 of 101 is also 101 because 1 will be an eigenvalue of m raised to 4 also. So m raised to 4 of 101 is also is equal to 101. Therefore, m raised to 4 plus m of 101 is equal to 101 plus 101. That is 202. So here we are using the first definition of eigenvalue. Okay. Any doubts?
No, ma'am.
Okay. So let us move to the next question. This is a question regarding the number of linearly independent eigenvectors of the matrix. We have to find the maximum number. This is a question from JAM 2023. Yes. 3 is the correct answer. Let us wait for some other answers also. So while discussing the geometric multiplicity of a eigenvalue, we have discussed that geometric multiplicity is the number of linearly independent eigenvectors of the matrix corresponding to the eigenvalue. So you can use that concept also while solving this. Yes. So let us move to the solution. So eigenvalues of a matrix like this means if a matrix of the form A0, 0B. So here we can see that this one is matrix A, this 2 by 2 matrix, and this 2 by 2 matrix is 0 matrix, and here also this is a 0 matrix, and here it is 2 by 2 matrix. So the eigenvalues of A0, 0B, this type of matrix is equal to eigenvalues of A union eigenvalues of B. So what is the eigenvalue of this matrix 1, 1, 2, 2?
0, 3, 3, 3.
Yes, 0, 3, 3. So if you are just taking this square matrix, then it is a rank 1 matrix, and so the eigenvalue will be 0 and this trace 0, 3. And this matrix, if you are taking, it is a triangular matrix, so the diagonal elements are the eigenvalues, so 3, 3. So hence 0, 3, 3, 3 are the eigenvalues of the matrix given. Now we have to find the maximum number of linearly independent vectors of the matrix. That is the dimension of eigenspace associated with 0 plus dimension of eigenspace associated with 3. That is simply the geometric multiplicity of 0 and geometric multiplicity of 3. So if we are taking the geometric multiplicity of 0, then we just have to find the null space of A. So if we are just calculating the null space of A, you will get that there is only one row with all the entries 0. So the geometric multiplicity of 0 is equal to 1. And the dimension of eigenspace associated with 3 is equal to null space of A minus 3i, because dimension of eigenspace associated with 0 means we are taking A minus 0 into I. A minus 0 into I means it is just A. That's why the eigenspace dimension of eigenspace associated with 0 will be the nullity of nullity of the matrix A. But here the dimension of eigenspace associated with 3 is equal to nullity of A minus 3i. So A minus 3i, when we compute, we will get this matrix minus 2, 1, 0, 0, 2, minus 1, 0, 0, 0, 0, 0, and 0, 0, 1, 0. So here we can see that first two rows are linearly dependent. So this is the reduced matrix, and in this reduced matrix, there are two 0 rows. So the geometric multiplicity of 3 is equal to 2, and hence the maximum number of linearly independent eigenvectors of the matrix is equal to 1 plus 2, that is equal to 3. Okay. Yes, so I hope that the answer is clear. Any doubts?
No, ma'am.
Okay. So let us move to the another question. This is a question from JAM 2022. Yes, it's option C. Yes, so it's just about computation. So let's start the explanation. Here we are given a matrix P, and given its eigenvalue 0, 1, minus 1. And further, it's given the eigenvectors also corresponding to these eigenvalues, lambda 1, lambda 2, lambda 3. So they are asking about the entry in the first row, third column. Okay. So suppose this is the matrix. P matrix is P11, P12, P13, P21, P22, P23, P31, P32, P33. Then the question is about first row, third column. That means P13. Okay. So V1 is an eigenvector of P with respect to lambda 1 means P10 is equal to 0 because AX is equal to lambda X. If there exists a non-zero vector X such that AX equal to lambda X, then lambda is an eigenvalue and X is an eigenvector. So we will get, since 1, 0, 0 is an eigenvector corresponding to 0, means P of 1, 0, 0 is equal to 0 into 1, 0, 0, that is equal to 0. This is a 0 column matrix. Okay. Now, V2 is an eigenvector of eigenvalue 1, means P of 1, 1, 0 is equal to 1 into 1, 1, 0. And 1, 0, 1 is an eigenvector of minus 1, implies P into 1, 0, 1 is equal to minus 1 into 1, 0, 1. Okay, now we need the entry of first row, third column, P13. So just take the first and third equation. From the first equation, we are getting P11 is equal to 0 because this matrix into 1, 0, 0 is equal to 0. So this implies that P11 is equal to 0. By computation, we will get. So now taking the third equation, P11 plus P13 is equal to minus 1. And P11 is equal to 0. So P13 is equal to minus 1. Okay. So hence answer is option C. Also, you can observe that P21 is equal to 0, P12 is equal to 1 from these three equations. So they are just asking about the first definition of eigenvalues, like AX equal to lambda X. Just asking the question related to the concept of eigenvalue and eigenvector. So I hope that the answer is clear.
Yes, ma'am.
Okay, so let us move to the next question. This is a question from JAM 2021. We are given a matrix A and they are asking about the largest eigenvalue of this matrix. Yes. 4 is the answer. So let us move to the solution. Here you can observe that row 1 and row 2 are same. So if two rows are same, then we know that its determinant will be 0. And we know that if determinant of a matrix is 0, then 0 must be an eigenvalue of the matrix. So one eigenvalue we got, it is 0. So 0 is an eigenvalue of A because determinant of A is equal to 0. Now what about the other eigenvalues? Just observe the sum of the matrices. The sum is equal to 4. All the row sum equals 4 and hence 4 is an eigenvalue of A. Okay. So we got two eigenvalues, 0 and 4. Now we have the another result relating trace and eigenvalues. Trace is equal to the sum of all its eigenvalues. So we will get that trace of A is equal to 2 plus minus 1 plus minus 1. That is trace of A is equal to 0, which is equal to sum of eigenvalues 0 plus 4 plus that third unknown eigenvalue. And so we will get X is equal to minus 4. So they are asking about the largest eigenvalue. So the answer is 4. So I hope that the solution is clear.
Yes, ma'am.
Okay. So this is another question. You can try it later. You can take the screenshot. This is a question from JAM 2021. And verify the answer is B. You can try it. Okay. So in today's session, we have seen some questions related to metric section of the IIT JAM syllabus. We have dealt with some questions related to system of linear equations, eigenvalues, and eigenvectors. And since I am focusing on IIT JAM, I am saying that next IIT JAM exam is on February 2026. So you have for all the JAM aspirants, they have enough time. So first of all, you have to set a clear target. This setting a clear target is applicable for all the aspirants. You just set a target. How much should I score in that exam? Maybe you will have some dreams and some aim, like I have to join in this particular IIT. So for joining in that particular IIT, you may need this much score in IIT JAM. So accordingly, and according to the cutoffs of previous year, you set a target for yourself and you just stick to that target. And now once that target is fixed, focus on the syllabus of the exam. So in that syllabus, you will have some strong areas, you will have some weak areas. So try to improve that weak areas. You try to read more on that weak areas, try solving more questions from weak areas, and also give importance to that strong areas also. From strong areas also, you should be able to do as much questions as possible. So strong areas also must be improved, or it should be also kept in that level. And weak areas also you should improve and you should come to that level by practicing, by reading, by understanding the concepts and all. And also practice a lot of questions. In this session also you can see that for each question, the techniques were different, because in case of eigenvalues, you can see that the most of the questions were related to eigenvalues and eigenvectors, but the techniques we have used are different. In some cases, we are using the determinant is equal to the product of its eigenvalue. In some cases, we use the trace is the sum of its eigenvalues, and in some cases, we are given a matrix, and in that matrix, there was some unknown, and we are finding it using determinant or using the trace or using the concept of eigenvalue. So to know this technique in a short time, because competitive exams, they are mainly assessing the time management also. So in that short time, you have to get the techniques to be used in that question. For that, we have to practice a lot of questions. And then prepare a short note also for revision. We just note down all the important result, counter example, mini formulas will be there. So just note it down for the quick revision and all. And also in this short note, you include problem solving techniques also. Like if you are given a matrix, which all techniques should be come into your mind by seeing that matrix. Maybe as we have seen, sometimes we have to reduce that matrix into upper triangular, or it will be similar to some of the non-matrices. So these are some of the techniques, and these techniques can be should be noted, and these techniques should come to your mind during the examination time. So practicing is very, very important. Okay. So these are some of the references for linear algebra. So be consistent, believe in hard work, and best wishes to all the aspirants. Thank you.
Thank you, ma'am.
Thank you, Ardra.
Welcome.
Ardra, please turn your video on and stop the presentation also.
Okay, sir. I will stop the presentation.
Okay, thank you, Ardra, for this nice session with a good collection of problems and detailed explanations of the theory. And also you have suggested an action plan and preparation tips for the learners. I'm sure that those who have seriously attended this session will get great benefits out of today's program. Now it is a time for feedback. Dear participants, feel free to share your feedback. All of you are encouraged to keep your video on and express your feedback.
Sir, there is one question.
Okay, you can answer the question.
Hello, ma'am. I'm not saying a question or something. I'm just a feedback. I really enjoyed your class, especially on a Sunday morning. We are not in a mood to listen to class and all, but the way you taught from like first you explained the concept and then the questions, that too like in a really simple way, actually made the morning very much like enriching, and it was light too. So thank you so much, ma'am, for the wonderful session.
Thank you for the feedback. Happy to hear the feedback.
Thank you.
Okay, others, if you have any queries, you can ask, and also you're encouraged to share your feedback.
I am Praveen Misra from Madhya Pradesh. Ma'am, collection of questions are very good, ma'am. Beneficial session, ma'am. Thank you.
Thank you for the feedback.
Thank you, Praveen.
Thank you, Praveen.
My name is Salagananda. I'm a final year student. Today's session is very nice. Even I'm poor in the concept knowledge, but the questions, all the questions I understand. Thank you.
Thank you for the feedback.
Good afternoon, ma'am.
Yeah. Yes.
I'm very grateful to attend your class, and this is a very fantastic class. And maybe after you will again take a class. Okay. I'm very thankful.
Agasraj, where are you from?
Sir, I am from Jharkhand.
Okay, okay. So, what are you currently doing? Which course? BSc
Sir,
or?
I am pursuing integrated BSc MSc in Central University of Jharkhand.
Okay. Yeah.
Thank you for the feedback.
Yeah. Others?
Hello, everyone. My name is
Hello,
Elsa.
ma'am.
Yes. Yes, Ivan. Yeah, Ivana, you can.
Hello, my name is Ivana. Ma'am, I really loved your class. The way you explained it was very simple and clear. Thank you, ma'am. And thank you, sir, for organizing the class.
Thank you, Ivana, for the feedback.
Elsa, you can speak now.
Hello, ma'am. My name is Elsa, and I'm MSc first year student. So I take this opportunity. Thank you very much, ma'am, because I was not much thorough in linear algebra in its basics. So I was very happy when Vinod sir suggested such a class was today, and your class was very wonderful. Last 2 hours were very engaging, and your questions has made me happy to do some. Now I am little bit sure that I can do some of the questions. And thank you to all, ma'am. Thank you, ma'am. And it's very helpful if you share the PDF that you were teaching in the class, in the group.
Sure, I will share.
Thank you, ma'am.
Okay,
Happy to hear your feedback.
Yeah. Any others?
Hello, ma'am. My name is Surya. I'm from Andhra Pradesh, ma'am.
Huh.
Your class is simply superb, ma'am.
Thank you, sir.
Surya, where are you studying now?
Sir, I completed my MSc, sir. I'm preparing now CSIR net and BEd, sir.
Okay. From where you have did your MSc?
2023, sir.
Yeah, from which institute?
Adikavi Nannaya University, Rajamahendravaram, sir.
Okay. Okay, all the very best for your
Thank you so much, sir.
studies.
Ardra, ma'am, one of your co-researcher, Priyanka, is my friend, ma'am.
She's my batchmate.
Yes, ma'am.
She's my friend.
Any others?
One question is there any book recommendation? I have shared, I mean, I have, in the last of my presentation, I have shared. Should I share now also again?
I think, yeah, I think they can take it from while we're sharing the recorded video.
Okay, sir.
By tomorrow or day after tomorrow, we will share the recording.
Okay, sir.
Hey, thank you, everyone. Thank you, Ardra, for this nice session. You have taken a lot of effort for preparing the PDF and all for the PPT and all that. I think it will be great if you could do more sessions on linear algebra on other topics like vector spaces and subspaces, linear transformations and all that. I know that you have all the busy schedules of PhD and all that, but if time permits, just think about it. If you could do such sessions, our participants will certainly get great benefit out of it. So anyway, please let me know your convenience. Yeah, in what message me in later. We can arrange such sessions if you are get enough time for preparing.
Sure, sir. Sure, sir.
Okay, thank you, everyone. Let us wind up here.
And thanking you all also for an interactive session.
Yeah, our participants have really enjoyed the session and actively shared the answers and all that.
Yes, sir. Yes.
So I request all the participants to attend such sessions in future also. And yeah, wishing you all the very best for your exams. Thank you.
Okay, sir. Thank you, sir, once again.
Let's sign up here. Bye.
Bye.